IBHL chemistry, the Arrhenius equation. Now what's fundamental to the Arrhenius equation is that a higher temperature speeds up the rate of any chemical reaction. That's any chemical reaction, no exceptions. And I've got a typical rate expression here. The rate of the reaction equal to the rate constant multiplied by the concentrations of the two reagents. A higher temperature must give a higher value for the rate constant K, because the higher temperature doesn't affect the concentrations of any reagent in the rate expression. Looking at the rate expression, if the rate is faster at a higher temperature, it must be that the higher temperature has raised the value of K. Rate constants are temperature dependent, and this can be used to calculate the activation energy of a reaction. A higher temperature speeds up the rate of any chemical reaction. It must give a higher value for the rate constant because the higher temperature doesn't affect the concentrations of any reagent in the rate expression. I've got my Arrhenius equation given here, as you would find it in the data booklet. Defining terms, K is the rate constant, R is the gas constant, EA the activation energy of a reaction, and T the temperature I'm stressing in Kelvin. A is called the pre-exponential factor. It relates to collision geometry. A more useful form of the Arrhenius equation is derived by taking natural logarithms. And again, straight from the data booklet, but I've written this in this format to make it easier for the next step. First off, I can see I need to calculate a value for K at different temperatures in Kelvin. So, for example, an alcohol reacts with an acid in an esterification reaction. I have my equation. I don't care that it's a reversible sign. 3 experiments, 1, 2, 3, with different initial concentrations of the two reagents, and the initial rate is measured. From experiments 1 and 2, the rate is proportional to the concentration of alcohol. If I look at experiments 1 and 2, concentration of alcohol doubles, the rate doubles within experimental error. From experiments 2 and 3, the rate is proportional to the concentration of acid. If I look at experiments 2 and 3, concentration of acid doubled, my rate doubled. That leads me to rate equals a constant, the rate constant, multiplied by the concentration of the alcohol and the acid. Rate is proportional to the concentration of the alcohol and the concentration of the acid. Introducing my rate constant allows me to write an equation in the form rate equals. K can be calculated from the concentrations and the initial rate for any of the experiments. If I look at experiment 1, for example, my rate is measured to be 0.0036. I have it. K is what I'm looking to calculate. But I can see my concentration of alcohol. I can see my concentration of acid. We can calculate K. Now, I will repeat this experiment to provide the following data. I'm repeating it at different temperatures in Kelvin. When I've done that, I'm recording the reciprocal of temperature. When I've calculated the rate constant, I'm calculating from it a value for ln K. Here's my Arrhenius equation again, and I'm comparing it with y equals mx plus b. This is why we rewrite the Arrhenius equation to enable that comparison to be made. So, when ln k is plotted against 1 over t, the slope is a straight line. The value of the slope is equal to negative EA over R. R is the gas constant, value given in the data booklet, and calculating the slope gives negative EA over R. You can see I've plotted in lines to enable me to measure rise over run. I can calculate negative EA over R, not forgetting that negative sign. From here, EA can be found. Note that the line slopes downward as it is negative EA over R. And EA, the activation energy, minimum energy required for a reaction to proceed, EA is always positive. Ln A would be the intercept on the y-axis. A is the pre-exponential factor. It relates to the frequency of collisions with the correct orientation. That's it. If you find that useful, please hit like. Please subscribe to be informed about future content.